So exam one, the average was good, but I know not everybody is happy with the score they got. So if you feel like, I think this is a good time to reiterate the sort of expected time commitment for this class. You should be putting in, there's 3 hours in class a week. You should be putting in at least 6 additional hours. So if you think of that as like outside of class, an hour a day, and that doesn't mean that's like the most common day you spend an hour. That means if there's a day that you miss that hour, you have 2 hours on another day, you know what I mean? So that's the expected time commitment. If you're putting in that amount of time and you're not happy with your score, first, you can come talk to me. Maybe there are some simple things that would occur to me. But the thing that I think really works well for people often is go through those practice problems, keep your work, and then bring your work into me, especially the ones that don't have solutions, but even the ones that do have solutions. And I can sort of walk through it with you and point out where I see things that are causing problems. I can ask you questions about it, try to gauge sort of what you're understanding well and what you're not. It takes a bit of time and effort to do that, but when people have done that in the past, it seems to have helped quite a bit. There were a few general comments that I want to make. These were things that I saw over and over again that are easy to fix, but you need to fix. The first one is in free body diagrams. The person looking at them should be able to tell from your free body diagram what vectors are parallel, what vectors are perpendicular, and what vectors are neither of those. Okay? So it should be apparent which vectors are parallel, perpendicular, or neither. If you're not drawing the directions of your vectors with enough care for someone to be able to see that, then you're not doing an effective free body diagram. Okay. Let me give an example of like the kind of thing I'm talking about. So for example, on that one where you had 2 boxes sitting on top of each other, I had people, well, even that is a little, so I had people sort of turning in free body diagrams that looked sort of like this, 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 this. That just doesn't help anything. That lets you count up the forces, it lets you count up the variables, but that's not showing the directions of those vectors. Okay, so I was actually, at the start of this class, I'm pretty lenient about that kind of stuff as far as points, but you got to get that straight now. Okay, that's an important thing that you need to get out of this class, is not doing your free body diagrams like that. So, no. The second thing, I can't really imagine ever taking off points for this, but it's a habit you should get into. Use vector symbols on vector variables. but not on scalar variables or vector components. So, for example, if this is the body, this is a vector variable, so use the arrow over the top. This is a scalar variable, so there's no vector symbol on that, even though that n, in combination with that unit vector I drew, is a vector. This variable n is not a vector, it's a number. So no vector variable there. And as far as components, so the vector variable f is equal to fx, fy, and those are each numbers. Okay? So no vector variables on the components, but on the vector itself, yes. Any questions about that? And then the third thing, I saw this with weights a few times. For vectors with known directions, so let's think of, for example, this vector times n, okay, is a unit vector shown by the direction times a scalar. So if you do your weight like this, a downward arrow, and then minus 98.1, what that really means is take that unit vector, multiply it by negative 98.1, and that is 98.1 positive going up. Okay? So don't, if you know the direction is this way, don't also use a negative sign. What you're doing is a double negative thing, and you're specifying the vector in the opposite direction of what you mean. Okay? Any questions about that? Okay, those were the main things that that I saw multiple times. Overall, the tests were good. Any questions overall about the tests? Or yes.
On number 4,
Mm-hmm.
when drawing that free body diagram, I found it kind of hard just with those angles to represent whether something was perpendicular or not.
Mm-hmm. Yeah.
Would you just recommend writing it if it's not?
No, I would just do it. I mean, just do it as carefully as you can. I mean, I think.
Yeah, because just with the way the angles were laid out, I found it odd to make it apparent that it's perpendicular.
Well,
In some cases.
sometimes things are odd and you still need to do them. You can exaggerate those angles a little bit. So that was shown at a, whoop, I'm drawing it the wrong way. That was drawn at a pretty shallow angle. But if you want to draw it at something closer to like a 30-degree angle or something, exaggerate that a little bit.
Okay.
So this force is upward. This force is downwards, 294.3. Those two are clearly parallel in this picture. And then you have a force here. I'll call that R left. That is clearly not parallel to the body or parallel to either of these two. And then you have a force over here that's clearly not parallel to any of those others. Okay.
Okay. I guess I just kind of found it odd to make it easily show that it's perpendicular to the slots and perpendicular to the wall.
Mm-hmm. Yeah, it can, especially with those pin and slot joints, it can be sort of tricky. If you want to draw in a dotted line or something,
Okay.
that is fine.
Not a big deal.
Yeah. On tests too, when you're under time pressure, it's harder. I know that. On homework, you should be careful about it. And if you can't do it freehand, just use a straight edge or something.
Yeah.
Any other questions about the test? Are there any problems anyone would like to see me do that you were confused about? Okay. So now today we're going to finish. Rigid body statics. We started to talk about. So back to rigid body statics.
Are you going to go over
The
the quiz at all?
quiz? No, I wasn't going to, but do you have any questions about that?
No, I was just.
Okay. I wasn't going to, but if you have any questions about it, please feel free to come talk to me about it. So back to rigid body statics. So we did one 3D rigid body statics problem, but we didn't start with it in its natural environment. We didn't start with the joints and go to the loads. So that's the last thing we have to talk about is how to treat joints in 3 dimensions. And that's sort of a tricky thing. So 3D joints. And I'm going to draw pictures, and I'm going to show these things, and I'll pass them around. And I'm going to go through everything in the same order I did with 2D joints. I'm going to start with joints that provide one variable to your equations. Then I'm going to go to joints that apply 2 variables, so on. So joint category 1. These are joints that introduce one variable to your equations. One variable into Newton's laws. There are 2 in this category, a frictionless contact and a roller. So the first one, frictionless contact. This one works exactly the same way it does in 2 dimensions. So if this is body 1 and this is body 2, a free body diagram of body 1 looks like this. The force is perpendicular to the surface of contact toward the chosen body, so like this. And if you draw a free body diagram of body 2, which I sort of have drawn as the ground, imagine isolating a chunk of the ground, and then the force is equal and opposite like this. The second one is a roller. But one thing that we have to make a note of in 3 dimensions is that this roller you have to picture as a ball now, not as a wheel. Okay, a wheel does something different. So this is like the balls on the bottom of like office chairs or something. So a ball, not a wheel. So I'll draw it sort of the same way, but the contact is on a ball. And I'll call this body 1 and this body 2. So free body diagram of body 1. The force is perpendicular to the surface of contact toward the chosen body. And then a free body diagram of the ground in that picture. Is that force is equal and opposite. In both of these cases, what do we know about the value of n? The ground can't pull on, in neither of these can the ground pull on, like body 2 can't pull down on body 1. So the way that I have these normals drawn, those values have to be positive. Any questions about either of those? So now joint, yes?
Sorry, for both cases means the frictionless contact and the roller ball?
Yes. That's right. That n has to be positive. Yep. So now joint category 2. These are the ones that, there's only one of these, but this one introduces 2 variables into Newton's laws. And there's only one of these. These are going to be 2 components of a force. And so this joint is a wheel with a preferred direction. So now this is making the distinction between a ball, roller, and a wheel. So you can imagine this wheel rolling along like a track. wasn't a great picture. Okay, so the wheel can roll along this track, but friction prevents it from moving perpendicular to that track. Okay, so let's think about what motions are allowed and what motions aren't allowed. Remember, that's always the way to figure out what loads a joint applies to a body. At the point of contact between this track and the wheel, does this wheel allow motion of body 1 along the track? Yes. So we know there's no force parallel to that track. Okay? That motion is allowed. Nothing's preventing it. Does it allow sliding perpendicular to that track? No. So we know that there's a force perpendicular to the track preventing that motion. Does it allow body 1 to sink into the ground? No. So we know there's a force perpendicular. Okay. Then rotations, we're going to assume that this is a single point of contact, and so all rotations are allowed. Okay, it can spin this way, the body can tip over that way, or it can tip over side to side. The only things that are prevented are a motion perpendicular to that track and a motion perpendicular to the ground. So free body diagram of body 1. There's a normal force. And there's also a force, I'll call it F perpendicular. That's the force perpendicular to the track, where these two forces are normal to each other. You could also think of this, if you chose a coordinate system like this, with the x-axis this way, the y-axis this way. So there's x, there's y, and z perpendicular to the track.
Did you want us to draw free body diagrams like with depth field in the direction?
That's not really going to ever come up. No. Do I?
Because yesterday or on Tuesday, you kind of.
I guess, yeah, actually, I guess I want you to draw, I think I want you to draw the outline the way it shows up in the problem. You know, so as it's not going to be a big deal, but I think it's going to be easier to convey the idea if you draw the outline as it's drawn in the problem. Yeah, drawing 3D free body diagrams is always kind of an odd thing, but do that the best you can. So you, instead of separating it up into this perpendicular force and this normal force, you can also think of it as a force component in the y direction and a force component in the z direction. What about the signs of these? What do you know about the signs of these two variables? Well, you don't know anything about the sign of that F perpendicular, that FZ. That can act in both directions to prevent motion. But that normal force, again, it can't pull down on it. So that normal force must be positive. Any questions, other questions about that one? Joint category 3.
One question.
Yes.
Couldn't N technically be negative if you had a wheel running in a track that was, say, on a ceiling?
Yeah, that would be a different thing. I suppose you would think of that as like a pin and slot joint.
Okay.
Yes.
You have to draw like a force acting on the track for joint category 2. Like we have force acting on the joint, but we have to draw force acting on the track.
Well, yeah, if you isolate the track, all of these are going to be equal and opposite. I'm not sure how many of them I have the. I didn't do it here because I just ran out of room. But yeah, all of any loads that are acting on one of them, you have equal and opposite loads acting on the other because of Newton's third law. Sure. Joint category 3 introduces 3 variables. And those are 3 components of a force. So that means that the joint in this type prevents all translation of the point in contact, but allows any kind of rotation. And the joint that does that is a ball and socket joint. Okay, so that's body 1, that's body 2. I have one of these here. So what the ball and socket joint does, if you think of the point that's in contact as being the center of the sphere can't go anywhere. No translations allowed. But this thing can rotate. It's a little tight. Made the tolerance a little weak. But imagine that it's frictionless. You can spin it like that, no problem. It can rotate like that, fine. You can rotate it like this, fine. And you can rotate it like this, fine. Okay? This is perfect, ready to go in someone's hip right now. Okay, so all translation is prevented. All rotation is allowed. No rotation is prevented. So free body diagram of body 1. We just have a full force vector, the force on 1 by 2. Non-zero, all 3 components are non-zero in general.
Are we ever going to have to worry about the fact that it can't rotate fully?
Nope, we're never going to have to worry about that. If you, like, that would be a design problem. So if you have a structure that's put together using a ball and socket joint that's locked like this, either you need to redesign that ball and socket joint, or they do, whoever sent you this problem, or there just doesn't need to be a ball and socket joint there at all. So we don't have to worry about it. But that's an important question design-wise, for sure. Any other questions about a ball and socket joint? That's one we're going to see a lot. Okay, joint category 4. This introduces 4 variables. And I'm going to do this, I'm going to write this as introduces up to these are kind of a pain in the butt. It introduces up to 4 variables. And those variables are as follows. 2 force components are always introduced. So always. And 2 couple components if they're needed for equilibrium. So this is the first one that we've seen where just seeing the joint isn't enough to immediately know what loads to put into your free body diagram. Okay, so I'm going to talk about that more, but in a way that's sort of a different kind of thing than we've seen so far. And the joint in this category is a pin joint without thrust. So you can think of that as, so there's one body connected to another body by a pin but there's no flanges on this pin to prevent these from sliding along the pin from each other. I don't have a single one of those here, but I have 2 of them. So this is 2 pin joints without thrust. Okay, it allows motion this way, like all pin joints do. It's capable of preventing motion. It's capable of preventing rotation this way. And in this case, because it doesn't provide thrust, it allows the 2 bodies to translate along the pin relative to each other. Okay, that's what the thrust would be the thing that prevented this kind of rotation, or this kind of translation. Okay. So let me label the coordinate system. So I'll call this the x-axis, this the y-axis, and this the z-axis. The z-axis is along the length of the pin. And I'll call this body 1. So a free body diagram of body 1. Looks like this. There is an x direction force component. There's a y direction force component. So I'll call this force on 1 by 2 x. I'll call this one force on 1 by 2 y. But there's no F12Z because if there was, that motion along the pin would not be allowed, and it is allowed. Okay. Any questions about that? And I still haven't, so this is a free body diagram of 1. I still haven't dealt with those 2 optional couple components. So what's up with those? Well, we know that, so this is a pin joint with thrust, but forget about that for a second. So we know that a pin joint allows a motion like this. Okay, we know it allows a rotation like this. So we know that there's no component of a couple parallel to that pin. Okay, but it doesn't allow rotation this way. Like it doesn't allow me to rotate this top piece out towards you. And it also doesn't allow me to twist the top piece. Okay? And so the axis of rotation, when I'm trying to rotate the top piece towards you, is an axis in this direction. So we know there's a couple in that direction. And if I try to twist it, that's an axis in this direction. So we know there's a couple in that direction. So these two optional couples are M1, 2, Y. And M1, 2, X. This is sort of, so the important thing here is that M12X and M12Y are only put in the free body diagram if they're needed for equilibrium. So what's an example where they're not needed for equilibrium? The one that's going to come up, the only one that's going to come up in this class, and the most common thing would be if you have two of those pin joints along the same axis, then if you think about what's preventing this smaller piece on the top from rotating, like if I try to rotate this small piece towards you, I'm not relying on the ability of these individual pin joints to prevent that rotation. It's not rotating towards you because I have a force here and a force here, and that's just locking it into place rotationally. So the rule of thumb is, the only time this is going to come up in this class is don't include the couples. For two coaxial pin joints. Okay. If you have two pin joints along the same axis, allowing the same direction of rotation, then just leave those couples out. Question?
For the free body diagram, the N and the F are both magnitudes, but we don't know the directions.
Those are components.
Okay.
So it's just saying that's a force vector and a couple vector, but both of them are 0 in the Z component. That's what it's saying.
So in our 2D version of that, we've got our X and Y, and then we put like a vector thing because we can just label it. But this, we have components because it's probably weird.
Right. Yeah, right.
But we still don't know the direction.
We don't know the direction. We just know it's in a plane. Yep.
Can you give an example about like if we don't include the moment for two?
Yeah, I will, but let me go through the list of joints first, and then I'll do some examples like that. Okay, next is joint category 5. How close are we getting to the end, would you guess? Nope. Much closer because there's only 6 degrees of freedom. So we can only get to joint category 6. If we have more than 6 variables, we can't solve it. You know, we only get 6 equations. At least halfway home.
You don't have four-dimensional statics problems?
I have never seen such a thing. That's a good question, though. Klein bottle statics.
Five? Didn't you just say five?
I did. I just got ahead of myself. I got so excited about being done. Okay, joint category 5. Introduces up to 5 variables. And these 5 variables are 3 force components always, and 2 couple components if they're needed for equilibrium. And the type of joint in this category is a pin with thrust.
What does thrust mean in this context?
I'll show it again. Let me draw the picture and then I'll show it again. Okay, so what this is a joint with flanges bordering it, so that that body, the one that I'm calling member 1 here, doesn't have the ability to move along that pin. So that's what this is. So this is a pin joint with thrust. So the one without thrust was free to move along its axis of rotation. This one can't translate because it has the flange on each side that prevents that. Okay, so it can rotate this way, but it can't translate in any direction now, and it can't rotate towards you, and it can't rotate this way.
So the more, I guess like a point of the way you're breaking down this is the more it can't move, the more forces it has.
The more loads, yep, forces or couples. That's right. Forces always prevent translation of the point in contact, and couples always prevent rotation of the body. Yeah, so the more loads you have, the more restrictive the joint is.
Oh, okay. So the more load is prevented from moving.
Right, right.
Oh, okay.
And so what's going to be joint category 6? It can't move at all. That's going to be a fixed joint. All rotation is prevented and all translation is prevented. Yep. Okay, so for this one, we have a full force vector. I don't know why I did that in green all of a sudden. So we have a full force vector on 1 by 2. And then if we need them, we also have a couple component 1, 2x, and a couple component 1, 2y. And this is with this coordinate system. X, Y, Z. Okay, so we know that it doesn't have a component about the z-axis. It doesn't prevent rotation about the z-axis. That's the whole point of a pin joint. But everything else can be, every other motion can be restricted by this kind of joint. So again, these couples are optional. Well, I mean, there are rules for when you use them. And how did I word it up here? Don't include the couples for two coaxial pin joints again. It follows the exact same rules for those couples. So don't include couples for two coaxial pin joints.
What's two coaxial pin joints with thrust look like? Would it just be the thing in the middle with two pin joints?
So I have one of each here. So we have, this is two coaxial pin joints without thrust. This thing's free to move. This is two coaxial pin joints. One of them does not have thrust. So if, I don't know if you can see that from here, maybe I'll pass it around. But on this side, there's nothing preventing that pin from sliding. But on the other side, there's two little flanges bracketing that pin, and that prevents this thing from moving along the pin. Okay. So here, I'm gonna just pass these around so you can see the difference between these. But those are two examples of coaxial pin joints. And if you see something like that, you never include the couples in the joints. Okay.
So if you had two coaxial pin joints with thrust, would the object in the middle be able to move at all?
Yes. Really what you would have there is you'd have a redundant limitation on the motion along the Z component, and you'd have to figure out a plan for how to treat that thrust, because really what you'd have is a statically indeterminate system then.
Okay.
The thrust only prevents motion along the axis of the pin.
Okay.
So if you have two things doing it, then they're just fighting over, like, I want to prevent more of it, you know.
And one
They don't really do that because they're joints. They don't have emotions. But
And one last question, that's just pin joints, it doesn't specify thrust or no thrust in this case?
for which one?
For,
Oh, right. No matter what, if you have
Okay.
any kind of pin joint, two of them coaxial like that, you don't include the couples.
Yep.
Because the forces prevent those rotations without the help of the couples.
If we don't include the couples, then we have like three force components, which is like three variables. But we need six. Does that work?
That won't work by itself, but if you have two of them, you know, and one of them has thrust, then you have two force components for one of the pins, three force components for the other pin, and then, you know, something else, maybe a cable or something. You have to have something else to put it in static equilibrium. But think about what would happen, I mean, mathematically, if you had two of these coaxial pin joints and you included all those couples. You'd have, for the one with thrust, you'd have 5 variables. For the one without thrust, you'd have 4 variables. You're already up to 9. You only have 6 equations. So that's going to keep you from solving the problem. And that's why you have to avoid putting in those couples if you have the 2 pin joints in tandem. Any other questions about that? Okay, so here's the easiest one. For statics, this is the easiest case you can get. Joint category 6. 6 variables are introduced. And those are 3 force components, and 3 couple components. The joint in this category is a fixed joint, or sometimes it's called a weld joint, but you know, anything where the thing is just stuck in place, it has no ability to move. I'll try to draw it. So if you have a beam like this coming out from a wall, where that thing is just totally fixed in place. This is body 1. So the free body diagram is made up of a force vector with all its components and a couple vector with all its components. Okay, so let's spend a little time doing example problems. These get so hard to draw. So, okay, let's say that we have a rectangular sign. And it's connected to the wall by a pin joint. No, not a pin joint. I've just been saying that too much. A ball and socket joint. And let's say that we have 2 cables connected to the top of this sign. So one's here and one's out at the end. And they're connected to the wall. And now I'm going to give a bunch of dimensions for this. So let's say that that first cable is connected 2 meters from the end of the sign. And then there's another ½ meter to get from that to the far end of the sign. And the height of the sign is 1.5 meters. And now the dimensions for the connection between the cable and the walls. So this distance is 1 meter. And this height is 1 meter. So that tells you where this cable attaches. And then from the pin to the other connection, sorry, this is messing up your picture, but let me just make it a little more believable here. Let's say this distance is 2 meters. And the height from here to the connection is 1.5 meters. Yeah. And that is all we need, I believe. So I'm going to label these points C, where that left cable is attached, and D, where the right cable is attached. And E, I'm going to call the center of mass. And then the wall connections are A on the left and B on the right. And we want to figure out what are the cable tensions. Well, what are the cable tensions? And what's the force vector applied to the sign by the ball and socket joint? And for a coordinate system, I'm going to use the x-axis that way, the y-axis that way, and the z-axis that way. X, Y, Z. All right, well, the first thing we need is a free body diagram of the sign. Anybody, did I rush through that too fast? You need to look at this more to write this stuff down? Or did you already give up?
You have the center of mass?
Yes,
Okay.
that's right.
I'm not clear on what's happening
Okay.
at the top. Back. With the,
There is a cable attached here
yep.
that's going to the wall on the left of the sign.
Okay.
And then there's a cable attached at the end that's going to the wall on the right of the sign.
Okay.
But they're both, so A and B are both on the same wall that ball and socket joint is on.
Okay. So yeah, it's the ball and socket joint that wasn't clear on.
Okay.
Okay.
So that little, square with the X through it or whatever, that's what the ball and socket joint is mounted to.
Okay.
Are there symbols for these 3D diagrams that we make up, like for the ball and socket? Is there a shape or something that you designated with, or fixed ones, or is it just told in the problem?
Yeah, I think it's just going to be told in the problem. Okay, so first draw an outline of the body. Oh, I didn't give a mass. There is a mass, 50 kilograms. If there wasn't a weight, all these forces would be 0. That would be easy. You could move on to the next problem. Okay, so acting at the center of mass, there's a weight of 50 times 9.81. At the ball and socket joint, what kind of loads are acting? Yeah, that just comes right from the list. Yep, it prevents all translation, so we have a force vector like this. I'll just draw unit vectors in the axis directions, and I'll write this as R. And then there are 2 separate cables. So there's a cable force going this way that I'll call that TB. The cable going to B, and then one here going to A. So that's a complete free body diagram. And now we're going to set up the table. Let's just go through and let's set up this full, let's set up the full table where we have the coordinates of the points where the forces are applied. We have the coordinate for the about point, the row vector, the force, and the moment. And let's just figure out what the coordinates are of all these points and set those aside for these calculations. So in that green coordinate system, let's first figure out the coordinates of that point A. How far in the x direction from the origin is A? 0. How far in the y direction? +1. And in the z direction? +1. So that point A is 0, 1, 1. That point B, how far in the x direction is it? 0. In the y direction? +1.5. And in the z direction? -2. The point C, how far is that in the x direction? +2. And then there's no y or z. The point D, how far in the x direction? 2.5, no y or z. And then the last one, E, is the center of mass. How far is that in the x direction? We're just looking for the middle of that rectangle. So 1.25 positive x direction. Y direction? -0.75. Z direction? 0. I don't know if you said that or not, but it's 0. Okay. Okay, so E is 1.25, negative 0.75, 0. And now we're just going to go through these forces. So I'll first do the reaction force R at the ball and socket joint. The location of that force is the origin. The about point, we might as well make it the place where we have the most unknown forces, so that's also the origin. Rho vector is 0. Force vector is Rx, Ry, Rz. Take that cross product and you get 0 for the moment. The weight force, that's acting at the location 1.25, negative 0.75, 0. The about point is the origin. So the rho vector is 1.25, negative 0.75, 0. The force vector is 0, negative 490.5, 0. And the cross product is negative 613, 0.13 in the z direction. So now we'll go that force produced by that cable going to A, that tension TA. The location where that's applied is, that's the point C, right? That cable force is applied to the sign at the point C. So the location where that force is applied is 2, 0, 0. About point is 0, 0. Subtract and the rho vector is 2, 0, 0. And now we have to think about that, the force vector applied. So how are we going to come up with the force vector applied by that cable? Yep, exactly. Yep, so we'll get a vector that goes to A from C. Then we'll find the unit vector in that direction, and then we'll multiply it by the variable TA. Okay, so that cable TA, we'll say the vector is equal to A minus C. Ooh, we're out of time. So that's 0, 1, 1 minus 2, 0, 0. That's equal to negative 2, 1, 1. If you take a unit vector in that direction, you get negative 0.816, and then positive 0.408, positive 0.408. And now we just multiply this by the variable TA. So our force vector is negative 0.816 TA, positive 0.408 TA, positive 0.408 TA. And then we'll do the same thing for TB. We'll start with a vector that goes from D to B. So a vector that goes from D to B is the coordinates of B minus the coordinates of D. So negative 2.5 1.5, negative 2. Let me just get this force down here, and then we'll stop. So the unit vector in that direction is negative 0.707, positive 0.424, negative 0.566. And so the force vector is negative 0.707 TB, positive 0.424 TB, negative 0.566 TB. Okay, so we'll pick up here next time. If you have time and you want to try going through it, take this stuff, put it in the table, and see if you can get through the equations.